In this video, we're going to talk about how to determine whether or not the conditions for binomial random variables are met by a certain situation. We're going to talk about what makes a binomial random variable binomial, and we're also going to look at how to find probabilities of a binomial random variable. So, a binomial setting is going to be a random variable that has the four following things true about it. First of all, binary. Their only possible outcomes are success or failure. There's only two. The trials are independent. It's the I. And the number of trials of chance process is fixed in advance. It's very important. We're going to contrast that with geometric setting later in the notes. But right now, binomial, you're going to fix the number of trials before you begin the process. And then the probability of success, it has to be the same for each trial. It cannot change depending on what trial you're on. If the four things are hit, the setting is binomial. If even one of those things is not true, then the setting is not binomial. Side note here, if you have three or more categories of events, you have to put those into success and failure. So for example, if you have roulette, success being landing on red, failure could be landing on green or black. So even though there's two different outcomes put into that failure situation, there's still success and failure only. If you want to see that binomial setting is useful, always check bins. So that's binary, independent, number of trials, and success. Always check those four. So if you were to create two situations on your own, I've created a couple. For example, if you were to say how many times someone rolls doubles in 20 turns of Monopoly. So 20 turns of Monopoly. How many times do you roll doubles? All right, we got to think about this. B, is it binary? Yeah, you can either roll doubles or not roll doubles. So binary, success and failure. Independent, are dice rolls independent of each other? Yes, they are. So binary, independent, absolutely. Number of trials fixed ahead of time? Yep, right there. And it's taken care of, 20 turns. And then probability of success. The probability of rolling doubles of a pair of dice is 1/6. It does not change depending on what turn you're on. So therefore, yes, probability of success is the same for each trial. So this would be a binomial setting. What wouldn't be a binomial setting would be how many days of the week it rains. So checking bins. B, the binary, success and failure. Yeah, rain, no rain. Independent, this is the issue. If you have independence, the initial conditions for each day are always the same. And if you had some kind of magical machine that controlled the atmosphere, you could put those into play. The problem is you don't. It rains on Monday, it may change the initial conditions for Tuesday compared to the Saturday. So therefore, the trials are not independent, therefore this is not a binomial setting. If you run through the rest, just to double check, N, is the days of the week fixed? Yes, 7. Probability of success? Again, the probability depends on what happened the day prior, so then therefore not independent, so this is a no-go, not a binomial setting. It's got to be binomial, success or failure, independent, the trials are independent of each other, number of trials is fixed in advance, and the probability of success is the same for each trial. So, binomial random variable and the binomial distribution. If the x is the count of successes in the binomial setting, that would call that a binomial random variable. So x, just like we did before with random variables distributions. The probability distribution of x is a binomial distribution. So it's a very simple name. It's a binomial random variable. Instead of a probability distribution, we call it a binomial distribution. There are two important parameters, n and p. N is number of trials in the chance process, and p is the probability of success. Possible values for x are whole numbers from 0 to n. So you can have 0 successes all the way up to n successes. N, of course, being the number of trials. If you have 20 trials, for example, you could have anything from 0 to 20 as your number of successes. You're going to be able to compute and interpret probabilities involving binomial distributions. So suppose there are 5 multiple choice questions coming up on a reading quiz in English class. There are 4 choices per question, with only 1 being correct. A person taking it didn't study and has no knowledge of the topic being assessed. He has to guess on each question. Also, each question pertains to a different topic from the other questions. Let's define X as the number of correctly answered questions on the quiz. Go through bins. Is this binary? Yes, you can have correct or incorrect answers. Independent. Are the questions and answers independent of each other? Is question 1 ending in question 2? Or question 2 ending in question 5? This sentence right here, also each question pertains to a different topic from other questions. That lets us know that each question is independent. So we can check that off our list. N, is the number of questions fixed before we start? The answer is yes, it is 5. Probability of success, is it the same for each question? The probability is the same, 1/4 or 0.25. So bins works out for the situation. N is 5, our two parameters, N and P is going to be 0.25, and that's just 1/4 written as a decimal. Because every four answers, there's only one correct, so the probability of getting right is 1/4. So let's find the probability of getting 1 right, or X equals 1. Let's write that as a sentence. Probability of getting exactly 1 correct. Okay, so you have to determine how many different ways can you get 1 question correct. Because you can't just do number 1 correct. You have to do, can I get number 1 correct and the rest of them wrong? Can I get number 2 correct and the rest of them wrong? How many different ways can you do that? So if we actually just map it out real quick, I'll show you. If you do first one success, the next 4 failure, that's one option. The first one failure, then success, then failure, failure, failure. That's the second option. And you just go through the list of possible situations for the quiz. I'm doing it very systematically so that I know that I'm sure that I don't miss any possible arrangements. This last one's got the first 4 are wrong and the last one is correct. So that's 1, 2, 3, 4, 5 different ways. So the 5 different ways is important because you have to find the probability of one way and then multiply it by 5. So the probability of X is equal to 1, or only 1 success. You're going to start this off by saying 5 times, and you do the probability of 1 correct. Well, the probability of success is 0.25, and that's happening 1 time. So the power of that's going to be 1. Since I only have 1 success, the power of it is only 1. If I have 1 success, that means I have 4 failures. The probability of failing is 0.75. And I get that because these two must add up to 1. Because either you have success or failure. That's part of the binomial setting. It has to be binary. So this is 0.25. This is 1 minus 0.25, or 0.75. And there are 4 failures, so this gets a power of 4. Let's write that out. So this is because there are 4 failures, and this is because there are 1 success. Or there is 1 success. And you multiply by 5 because there's 5 different ways to actually do 1 success and 4 failures. And when you multiply that out, you get 39.6% chance of getting 1 question correct. So not all that unlikely, 40% almost. It's almost a flip of a coin if you're just blindly guessing on a quiz. Now, let's talk about this number here, this 5. Where does that come from? Well, it's actually called the binomial coefficient. It's the number of ways arranging k successes among n observations. So k in this case was 1. How many different ways do we figure out how to arrange 1 success out of 5? That's what we did up here. Now, if you have a large n, like 100, and you want to arrange 30 successes, this is going to take you all afternoon. So we outsource that job to what's called combinations. And you've learned about this in Algebra 2 a little bit. It's the number of ways, also looks like this in the calculator, NCR. It's the number of ways to arrange k from n. it looks like this, n, k. It's not a fraction now with parentheses. The formula is n factorial over k factorial times n minus k factorial. We are not going to be using this formula. We're going to use the calculator's formula or program to do this for us, but understand what you're doing. You find a number of ways of arranging k successes out of n observations. And this will be just in front of your probability at all times. So our probability formula, if we have k successes, it'll look like this. The probability of x is equal to k. So k in the previous example was 1. The first part of your function or your equation is going to be the number of ways you actually can arrange that many successes times the probability of success, p. And you're going to raise p to the number of successes there are. So if k is equal to 3, that means you multiply p 3 times. So whatever the number of successes are, that's the power of success. So if I have k successes, I raise the power of success to the kth power. You're going to multiply that by the probability of failure, which you've already talked about is the complement of success. So success is a probability of p. That means the probability of failure is 1 minus p. And this is going to be raised to the power of n minus k. Now, it may look complicated here, but let's just talk about this for a second. If there are n trials in k successes, we subtract that from the total to find how many failures there are. So if there are 10 trials and 4 successes, that means there are 6 failures. So that would be 10 minus 4 to get 6. Okay? So if we do the colored version here, maybe a lot more helpful. This is the possible combinations of k from n, so number of ways you can actually be successful out of n. It's the probability of successes raised to the power of the number of successes. Probability of failure raised to the power of number of failures. These two powers must add up to n, or total number of trials. So when you add these two powers together, it should be a total of n. So if n is 20, these two powers have to add up to 20. Similarly, p, 1 minus p, must add up to 1, because they are complements of each other. Remember that n is the number of trials, k is the number of successes. So let's go back and recalculate for a different example, or a different probability. This is the same situation, probability of x equals 3 now. So my k value is now 3. So here's what it looks like. It's 5, choose 3 in the combinations. The probability of success is 0.25. And there are 3 successes. The probability of failure is 0.75. And there are 2 failures. If there are 3 successes, there are 2 failures because 3 plus 2 must add up to 5. The number of total trials. So when you do that, and you type this in your calculator, the number of ways to arrange 3 things out of 5 is 10. 10 different ways. And then I'm just going to rewrite these down here. And when you calculate it all out, you get 8.79%. So conclude your answer with context. You could simply say, there's a 8.79% chance that he gets 3 out of 5 questions correct. Very simple sentence if I ask for context. What about instead of doing an equal to, let's do an actual inequality. So probability of x is greater than 3. Well, this one involves more than one probability. If x is greater than 3, you have 2 options. You have the probability of x is equal to 4 and x is equal to 5. And I stop at 5 because that's the max, because there's only 5 questions. So you're going to do 2 different probabilities here. So the number of ways to arrange 4 correct questions out of 5 is this combination here. There are 4 successes. So I'm going to raise 0.25 to the power of 4. I'm going to raise 0.75 to the power of 1. So this is the probability of x equals 4 plus the probability of x equals 5. That's 5, choose 5. It's actually only one way, but it's just a formality so you can look at it, how it's the same throughout every probability. 5 successes and 0 failures. So you'll notice that This is raised to the 0th power, which means it turns into 1, or we don't write it anymore. The only way you can choose 5 things from 5 things is one way. So that ends up being just 0.25 to the 5th power. When you actually multiply that out and then add the two terms, you get 1.56% chance. So you could say there's a 1.56% chance of him getting, and this is strictly more than 3 questions correct. And this really only works for the probability that's binomial, this equation here. And it's got 3 parts to it. Just remember, it's a number of ways you can actually arrange the successes, times the probability of success raised to the power of how many successes, and then times the probability of failure raised to the power of how many failures there actually are. These 2 probabilities must add up to 1. These 2 powers must add up to n. In this case, it's 5.